Good morning. Well, we are back to chapter 12. We had said that chapter 12 divides up. Kind of the first half of the chapter is looking at something called static equilibrium, and we looked at a good number of problems there. I hope you guys are looking at the homework problems. As we said at the end of last lecture, understanding how to identify lever distances and then using those to set up the torques, that's really important. So practice with these homework problems, practice with the examples that we've looked at. This second half of chapter 12 is looking at the elastic properties of materials. And we're going to look at the things that are called stress and strain. And I have to say, I continue to get these backwards. If I get them back, I'm going to really pay attention and not get those backwards. I really wish they would change the names of stress and strain. Anyway, here goes. If we have a support structure, here's our support structure. Now, it used to have a certain length L. So L was right here. And what happened was we took an object and we attached it to that support structure. Now, as a result, the structure got stretched out. Everything stretches a little bit. Even if this was a steel column or a steel cable, it's going to stretch a little bit, and that little bit of stretch is called delta L. Now, this is where I have issues. The amount that the material deforms is the strain on that material. So the material now is straining because instead of being its natural length, it has been stretched out. So that delta L becomes the strain. Now, what is it that caused the delta L? And what caused the delta L, what were forces? So there's a force now pulling down on the object, and if I look at the object itself, this is where we really should have two force diagrams, right? So this lower object has a mass of mg, and mg is pulling down on the object, and that should be centrally located over here. And then there is a force, F, lifting up on. So the green forces are acting on this object. The indigo forces are acting on this structure. So this structure is being pulled down with force F. Now the force of F equals mg because it's a static problem. So F is going to be here. Now what gets left out and forgotten is that I can't just pull with F on this side. There's got to be another force up here holding on to that vertical structure. I need a force in both directions. If the force in this direction is not balanced by a force here and vice versa, then this object begins to accelerate. So I just want to make sure in the force diagrams, make sure that you're getting all the forces listed. Otherwise, conceptually, you'll start to get confused about how these objects, what forces are acting on them. So again, it's a conceptual issue here that this object is not accelerating. So if we exert a force on it on this end, that's going to set off some kind of a force in the other direction. We're going to create a stress in the other direction. So the forces are referred to as, the forces are related to stress. We'll see it's a little more complicated, but it's the forces that are the stress, and the strain is the amount that the material changes shape. We're going to fine-tune those definitions here as we go along. But anyway, keep track of what we want to be able to do is keep track of the delta L's. So that is what it's all about. So here's a diagram showing what happens with materials like the one before. What happens when you do start stressing them? So if we took this object, this support structure here, and we attached an object to it, and we attach another object, and just kept increasing the mass, what will happen is that the delta L will increase. So with these structures, if we continue to stress them with larger and larger forces, eventually the materials will fail. So if we're building a bridge or we're building a building, we want to make sure that there's enough material strength in place that the materials they're not overstressed. So here's a diagram showing how that works. So to me it's kind of backwards, but this is kind of standard for how these are done. What we got on the vertical axis is actually the force, and then how much has the material stretched out. So I'm going to say that this is what we actually control, right? We determine how much force. What we can do is take a material and exert larger and larger forces on it until it fails, until it stretches out so much that it doesn't recover. And so there's what's called an elastic region. So if I keep exerting a larger and larger force, what I find is roughly a proportional elongation. And that's what our formulas that we're going to be looking at are going to tell us, is that we'll get a proportional delta L. A delta L is proportional to the force being applied to the structure. Now there's a limit. So once we get outside of what's considered to be the proportional region, there's a proportional limit. And at that point, the material begins to elongate even more. So, we steadily increase the force and the delta L gets bigger. But then the material gets a little soft. It gets, it starts to stretch out more easily. And that says we're past the proportional limit, and now it's beginning to stretch even more. And then there's what's called the elastic limit. The elastic limit says, look, if you stretch it out more than this, it cannot recover to its original length. The idea is that, up through the proportional region, up to the elastic limit, if we back off, if we remove the stress, then the object recovers. It goes back to its original length. But there's an elastic limit where that won't happen. We pass the elastic limit, and we go into what's called the plastic region. Now the material is kind of flexible. It's stretching very easily. Notice that we're really not providing much force. We kept increasing the force, increasing the force, increasing the force, and the material was fine. It is recoverable up to this point. As we exert more force, we just get a lot of elongation. The material now just begins to stretch out, and there's no way it's going to go back to the original shape that it was constructed to be. And then at some point, notice there's this really long plastic region, and that's just coming from a little bit of extra force, and then it snaps and it's broken. So it's completely failed at that point. So that's a model of how materials behave. If I've got a piece of steel, a steel cable, or an aluminum support structure of some sort. When you take the material science class here at Laney College, you get to try all this stuff out. You get to generate these curves. You get to take little pieces of steel or copper or whatever samples they have and stretch them and see where the proportional limits, the elastic limits, the plastic region, and the breaking point. You get to see all that and experience it close up. So the formula that we're going to come up with to represent everything that we just talked about, this only applies to the proportional region. So this form, and that's, if you're building a bridge or building a building, you kind of build it for the proportional region. You want to stay away from this elastic limit. You don't want to get anywhere near that where the material is going to be overstressed and permanently altered, I guess. So the delta L here, great. So that says stress. It's supposed to say strain. So cross that out, replace that with strain. I'm going to go back and do a few edits here yet on these slides, but this is to keep you on your toes, right? So I apologize for that. So this is the strain, the delta L and the L naught. And this is what's called the elastic modulus. And so that's why people major in engineering, is so you can say cool things like elastic modulus. What's the elastic modulus of stainless steel? And that tells you how it responds. That's the proportionality factor. It tells you how it responds to stress. So the stress here is not force by itself, but force per area. So if I build a structure, but I build it bigger, it's going to more easily accommodate the force, and so there won't be as much stress on it. So it's force divided by cross-sectional area, and the L naught and the delta L are strain. All right, here's a whole table. So if we look at all the different ways, well, not all the different ways, but the ones we're going to look at, there is what's called the elastic modulus, also referred to as Young's modulus. I don't know how Young got hold of that. But here are different materials. Here's iron, here's steel, brass, aluminum, concrete, common building materials here. Ooh, they even have pine wood. And then they have bone, which is kind of interesting. So the formula we just looked at is for what we consider to be an elastic stress, or a tension or an elongation. Now shear, we're going to find out, is kind of a sideways stress. This is a stress right along the direction the force is being applied. And then there's a bulk modulus. We should probably come back to this table once we've looked to see what these different stresses look like. So coming back to this formula right here, let's look at one of the examples. It's a tension in a piano wire. So I have a piano string, I think is what they're called. So this 1.60 meter long piano string, I guess they really are wires, has a diameter of it looks like 2.0 millimeters. So the wire itself has a diameter of 2 millimeters. What is the tension in that string if it stretches 0.25 centimeters when tightened? Now, let's take a look and see. We've got all the numbers from here. So, and a piano wire, or a piano string, that's pretty narrow. So here's our piece of steel. So here is this steel wire. And remember, when we tension it, there's going to be tension in both directions. And the tension gets set up throughout. So when you say, well, what part of the steel wire elongates, which part of it gets longer? All of it does. So there's a little bit of stretching here, and a little here, and a little here, and a little here. So it's proportional throughout. If we're going to take it and extend it by 1%. So the wire right now is 160 centimeters. Stretching it by 1% would be 1.6 centimeters. And that would say that every section of this wire that we look at, if we subdivided it and measured how much this part stretched, well, that stretches by 1.6%. And this section stretched by 1.6. And so the stretching is throughout the material. Probably something, when you hear that, you go, well, of course. But it's something to remember when you're looking at these problems. Now, the combined delta L that takes place throughout that entire length works out to be 0.25 centimeters. Okay, so we've got the L, we've got the delta L, those were both given. And so let's take a look at how much strain that represents. Strain is delta L over L. Remember, strain is asking how much, proportionally, how much elongation, how much of a change in shape does the object undergo? And so strains are unitless. We take the delta L, divide through by the L, make sure that the units are the same so they'll cancel out. For the example they've given us, the strain is 1.56 10 to the minus 3. The delta L compared with the full L is 1.56 10 to the minus 3. I always like to take inverses, I don't know why, but this would be 1 part in 640. So I'm getting 1 part elongation for 640 pieces of length. If I divided the length up into 640 pieces, I'm getting enough elongation to add 1 more of those pieces on. And the strains are going to be unitless. Now here's the whole formula here that we wrote down. The delta L is 1 over, remember that's our proportionality constant. And for that, we looked that up for the material. This, we were told, is steel. So going back to the table that we looked at before, here is that table. And it says in the table that the elastic modulus for steel is 200 billion newtons per meter squared. Now I've noticed in the engineering text now that instead of newtons per meter squared, they've started using pascals. It's kind of interesting. It is unit of pressure. Newtons per square meter is the same thing as units of pressure. I still kind of prefer newtons per square meter. Pascal to me certainly applies to solids, but I always feel this is kind of, anyway, it's a unit issue I have to get over, I guess, but newtons per square meter, I think when you take the materials class you're going to be learning this in pascals, but these elastic modulus for common building materials, as you see, it's in the billions of newtons per square meter. Now it doesn't say that the material can survive that much stress. This is the proportionality constant. So if we get back to where we are here, what it's saying is in order to create a certain amount of strain, so the strain we were able to determine, that 1.56 10 to the minus 3, if we multiply that strain by the elastic modulus, that will tell us how much stress we need to apply to create that much strain. The bottom line here is that the elastic moduluses and the shear modulus and the bulk modulus, they're defined in a way where the larger values of E, G, and B mean that the material is more rigid. It doesn't stretch as much. So you can see steel's like, you know, the largest value on here. So of all the values listed, aluminum, brass, and aluminum aren't really going to compete with, they need like titanium or something on here, right? But steel has the largest elastic modulus and the largest shear modulus and the largest bulk modulus. So steel is very difficult to create a strain in. It doesn't strain very much, even under a large stress. So here's what I looked up, and look, I even put the gigapascals in there because this is 10 to the 9th newtons per square meter, so that would be 200 gigapascals of stress. Now, what I did then is I took the stress and I divided it by the, I took the elastic modulus and multiply, so I'm just following the formula. I put in the elastic modulus, I put in the strain that we had calculated, and it says that the stress that this piano wire is under would be 313 10 to the 6 newtons per meter squared, so that's the stress. And now I've got to separate out the force. So this is the stress, but I've got to calculate what the area is, so I managed to fill it in right here. I had some extra space. The diameter of the wire was 2 millimeters. The area of a circle is pi over 4 diameter squared, and so I ended up with an area 3.14 10 to the minus 6 meters squared. The stress looked enormous, right? It was in the millions of newtons per square meter. When I turn it back down into a force, I go, well, yeah, the force is, 980 newtons. So, you get out that piano tuner and you tighten the whatever, whatever the wires are attached to. And so this wire has been tightened to about, almost 1,000 newtons. Now 1,000 newtons would be about 200 pounds of force. Seems like a lot. I don't know if that's a typical tension in a piano string or not. 200 pounds does sound like a lot. All right, on the formula that we've just looked at, so what they've done here is solved for the elastic modulus, and said the modulus is stress divided by strain, which is what we talked about. And so the stresses, the forces we've been looking at so far, have been forces that tend to elongate the material. This is referred to as a tensile stress. Forces that tend to stretch the object out are tensile. And so the elastic modulus covers tensile stress in objects. Now, compressional stress is different. Compressional stress is different from tension. When we look at this structure, all this stone, which is kind of remarkable, all these stone structures are sitting on top of each other. Now, what's the effect on, for example, this column right here by having all of this weight sitting on top? What is that? Well, with all the weight of the stones sitting on top of this column, that's going to tend to compress it. So these columns are all pushed together. We've got forces from below pushing up on the column, and we've got forces from above pushing down on the column. And a lot of materials like stone are very sturdy under compressional stress. This is not tensile, it's compressional. So it's in the other direction. So in this case, if I'm building a building, most of those structural, well, we've got to go back and look. If I'm just stacking things on top, the forces are going to be tending to compress objects. So if we go back and look at this building one more time, right here, we could ask, well, what about the stone here at the floor? What's going on with that? Is that under compression? And we would say yes. Where the columns come down and are resting on that floor, the stone underneath that is also being compressed. It's being pushed up by the foundation and pushed downwards by the stone, so it's caught in the middle. It's also going to be undergoing a compressional stress. And this is what the pictures look like. So those earlier examples with the piano wire and hanging objects vertically, those were creating tension in the structure, and the delta L's, things were being stretched out, we're getting additional delta L's. When things are under compression, the delta L is in the opposite direction. The delta L's, the objects are getting shorter. I guess that's the bottom line here. So under compression, the delta L's are telling us how much does it shorten. So we don't worry so much about signs on these. We're thinking just in terms of amount. So when we look at the diagrams, the delta L here would tell us how much stretching we're getting, and if we use the very same formula, here the delta L would tell us how much is it being compressed. Now, there was a shear modulus in that table, and shear modulus has to do with pushing from the side. So let's say we've got a building or a structure or a textbook. Textbooks are good for this because you can say, okay, here's a textbook. What would happen if it underwent a shear strain? And a shear strain would change its shape. Now it's back to normal. Now there's a shear stress on it. And so the shear stresses, I've got a force that's to the side here, and then at a different location, the opposite direction. So what it's doing is it's tending to tip the object, or it's straining the object by an amount delta L. Now, the L naught in this case is the length of the object in a direction perpendicular to the delta L. So in the tension case and the compression case, here, the delta L direction and the L naught direction, those line right up. But in this case, the delta L's are perpendicular to the L naughts. Something to be, oh, there we go, there's a textbook right there. And so what we've got on this book right now is there's a force on this end of the book, and there's a frictional force holding it against the table in the opposite direction, and the book strains in that direction. Same thing here. I think what they're doing is they're suggesting at least that it's proportional to L naught. The L naught would be from here to here for a shear stress. And here the L naught is shorter, and as a result, we're not seeing as much delta L. The delta L is proportional to L naught. So as this stack of pages gets thicker and thicker in a book, you're going to see, the L naught's going up, and the delta L would go up proportionally for the same amount of stress. Now, for the shear strain, for the shear modulus, we use the symbol G, which is not sure where that came from, but the rest of the formula looks the very same. So the formula here isn't any different. I think we have an example with the shear modulus, maybe not right away, but later on. And certainly in the homework, take a look at some of the examples there. There's also what's called a bulk modulus, and the bulk modulus B applies not only to solids, but the bulk modulus applies to fluids. And so water, for example, if we go back to that table, we're going to find that there is a bulk modulus, there it is, for water. So here are the shear moduluses. Now they didn't give shear moduluses, that's kind of interesting. Concrete, brick, marble, not sure how they deal with shear. That's a good point. Concrete, for example, so even though with the elastic modulus we're saying this applies to tension and to compression, that's not really true for a lot of materials. Concrete, for example, very, very sturdy under compression, not so under tension. So concrete, we don't want to make a cable out of concrete, but if it's a building and we're stacking things where things are going to be compressed, concrete is very, very sturdy. So you should really take these columns of Young's modulus and separate them out into tension elastic and compression elastic. And then here are the shear values, and then here are the bulks, and notice the bulks also apply to fluids, and so we have water, alcohol, and mercury. It applies to liquids. And bulk modulus has to do with compressing the entire sample. So this has to do with how much does the volume change when we place it under a lot of pressure. So if we put it in a region where there's a lot of pressure pushing in all around the object, how much does the volume decrease? Well, if we take a block of iron or steel and drop it into the ocean, as it drops farther and farther, the pressure is going to be going up. We'll see this in chapter 13. And as the pressure goes up, the steel shrinks. Well, it doesn't shrink. Yeah, it gets compressed, let's say. It's compressed by the pressure of the water. So the volume of the steel goes down somewhat, slightly, when it's compressed by those fluid forces. Now, there's also this issue we talked about where the material fractures. It fails, it breaks. And so under tension, that usually looks like, the material just splits. It fractures through. Here, we start to see fracturing take place within the material itself. With shear, we can have fracturing along layers parallel to the forces. Now, what's interesting, I had to highlight this part. When designing a structure, it's a good idea to keep anticipated stresses less than 1/3 to 1/10 of the ultimate strength. So materials have what we call an ultimate strength. There is a stress under which the material fails, it fractures, it breaks. And they're saying it's a good idea to make sure the stresses are within 1/3 to 1/10, and I'm going, yeah, that is a good idea. You don't want to go right up to the edge of when the material is going to start to fail. So you want safety factors. And you guys, in your engineering classes, you will have to know what all those safety factors are. So we think of safety factors as, they're saying at least 3, and maybe more likely 10. Okay, this is another table that looks like the table before. Do not get them confused. Make sure that when you're flipping back and forth through the textbook, this is not the elastic and shear modulus table. It's the ultimate strength. Now, ultimate strength tells us under what stress the material will fail. If the stress gets to a certain point for a material, it's going to fracture. And again, steel comes in pretty good here, much better than just regular old iron. So doing an alloy and making different types of steel is good. Brass is doing pretty well. Aluminum is doing pretty well. Under tensile strength, see, concrete just fractures. So concrete is not very sturdy under tensile strength. And so maybe these are the two columns I was thinking in terms of, I guess, ultimate strength, but even under the amount of elongation, I don't know, I'd have to go back and look and see what does happen to concrete if we try and stretch it out. Anyway, its compressive strength is 10 times as large as its tensile ultimate strength. And then here is shear strength. So shear strength is showing under shear stresses what's the maximum shear stress this material can deal with. Okay, so here's the piano wire again. This time we're going to break it. Yes, okay, this is breaking the piano wire. Same piano wire as before, 160 centimeters, diameter of 2 millimeters. How much tension was it going to take to break the piano wire? We got to go back. Where was the piano wire before? There it is. Okay, how much force is it under right now? And it says 983 newtons. Is that going to break the piano wire? Apparently not. Well, let's see. So it says that this would be a tensile strength. So we're looking at steel, and we're looking at the tensile strength column. And it says that the largest stress this piano wire can deal with would be 500 million newtons per meter squared, or 500 megapascals. Now, remember the cross-sectional area, we solved this before, 3.14, 10 to the minus 6 square meters. And the stress now that we are applying is force over area. That says that the force then we can think of as the stress times the area. Now, from the table, that table is telling us the maximum stress. So it's not a maximum force, right? If we can't say what's the maximum force that steel can survive. It depends on how big the piece of steel is. So that's why the factor of the cross-sectional area is there. And the maximum strength, or the ultimate strength, is actually the maximum stress that it can handle. So if we get up to a stress of 500 million newtons per square meter, that's going to fracture the piano wire. Now we take that stress and multiply by the area to find out how much force that would be, and the force came out at 1570 newtons. So it seems like that first piano wire example we looked at was still safely within, I guess, it's certainly not a safety factor of 2 or 3, but I guess if a piano wire snaps, a building doesn't fall down. So it's not quite as serious as the stress in the cables on the Bay Bridge or something like that. We could have a piano wire that would snap, which, that could be serious in a concert. You have to stop, work around that fracture, I guess. And I think piano notes have multiple wires for each. Anyway, I digress. So this is 1570 newtons. That's, once we tighten it to 1570 newtons, sproing, the wire's going to snap. All right, here we've got a horizontal beam. And so here's a beam, and what they're showing with this is kind of interesting. A horizontal beam can be under both tension and compressive stress, either due to its own weight or due to the way that it's being loaded. So it needs to be made of a material that's strong under compression and tension. So let's see. So what's happening is this beam is being supported at this end, it's being supported at this end. Now it's got its own weight, and then it could also be loaded. We could be setting stuff on this beam, and as a result, it's going to bend a little bit. This creates a shear stress in that horizontal beam. Now, what happens with this material is the lower part of the material ends up stretching out. The top part of the material ends up being compressed, and the dashed line that they drew roughly through the center of the material is going to be the same length that it started out to be. So that middle line stays the same length. I get an extra delta L down here. I get a reduced delta L here. And so we're looking for something that's sturdy enough under compression and under tension in order to build structures. Now, here's an example that the book talks about at several points during the chapter. There was a convention center, I believe this was in Kansas City, and a simple enough miss by one of the structural engineers, and I don't know the whole story here. I don't know if it was a miss by a structural engineer who signed off on this design change, or if it was just the people actually doing the construction at the construction site decided this would be equivalent. In any way, there were walkways, a couple of supported walkways over a big open area, a big kind of ballroom, convention room kind of area where people could just wander around and meet each other. And there were these walkways up above where people could kind of look over and see what was going on down below in that open area. And the original plans had called for a support structure to come down, and there were a series of these support structures coming down. So there was a whole series of them, and then there was a walkway where people could look out over the open area. At what they're labeling as point A here, and equivalently here, for the upper walkway there was a pin that would go in, and then on the lower walkway there would be another pin. What they found was that these vertical structures were hard to bring into the building. So it was tough to be able to get these installed at the length that they were originally intended to be. And so somebody came up with an idea, and it turned out to be a really unfortunate idea, that you could actually cut these. Someone said, hey, let's do this. Let's cut the supports. And then what we can do is we can we can put a bunch of supports in place, and then get the first walkway built, and then we can take the cut sections, add those on at the bottom, and then build the lower walkway. And that's what they did. And I think it was for a year or two, this worked. But at one point, it became overloaded and collapsed, and people went back and looked at this and realized what had happened. So with the original plan, the pins would have a force of mg. Now mg corresponds to the gravitational force on a section of that walkway. So here is a section of the walkway, right here, and it's got a mass m, and that pin is responsible for supporting this much of the walkway. Well, that meant that the pin had to support mg here, and the pin had to support mg here. And it was designed to do that. Now, what happened is that this pin, once you broke the support structure, then this pin right here, let's start with the lower one. So the pin here is supporting mg, and that means that this pin also has a stress of mg, and that's pulling down, but it's pulling down on the walkway. So it's pulling down on the walkway itself, and that means when this upper pin goes in, it's not just supporting one mg, it's not just supporting the mg from the upper walkway. This pin is also supporting the mg of the lower walkway, because the support structure has been cut and the mg from here is being supported through that pin. So it doubled the stress on each of those steel pins that were put in to support the walkways. Now, the slides here have been saying, it's always a good idea to maintain a safety factor of at least 3. This failed because the stress on that pin doubled. So, and I don't know how the walkways were loaded when the collapse took place. Maybe there were more people crowded onto the walkways than anyone had foreseen. But in any case, this is a picture that shows up at a couple different times in the text. And there were over 100 deaths, I think, from the collapse. So, so these are the things you really have to watch for, right? And this is, my own diagram, but saying basically the same thing as what we just looked at. So you really do have to pay attention, and this is, if nothing else, this is a reason that you double and triple check, and you go and you talk to another engineer that you're working with, and if you're involved in the construction side of things, you make sure that you talk this over, think about things carefully before you write up the initial plan, and then definitely, this was a change made just before construction. So definitely stop and think about any changes that you're considering just before something is, while something is being built. All right. Here is an example of a bridge, and it's referred to as a truss bridge. And so what we've done here is you can build a bunch of triangles and put them together with pins. So the joints here are steel pins that have gone through, holding the separate steel pieces together. And you can see that they've done kind of the same thing with this ceiling support piece, with this truss, and here in my garage here, and in my, you see these all over. Now this is a bridge, and so you can actually go in and analyze forces acting at each of these joints. This is kind of an interesting example to take kind of a look at here, so let's do that. So what's happening with these trusses is that each one is going to be under tension or compression. Now what they've done is they've said that the mass of the structural pieces themselves is small. So if we neglect the gravitational forces acting on the pieces themselves, then the forces will line up along the structures. Now that wasn't true earlier in the chapter when we were looking at some of the hinges and the support pieces that we were looking at there. So there we had some weights that were included, gravitational forces. Okay, so let's take a look and see. So for this example that we have here, what we've got is the very same bridge that they showed us. Now it's simple enough. We've got it built out of these, we've set up these triangular pieces. And the idea of triangles is, once you put pins through each of these triangular pieces, it's rigid. A triangle won't shift. You can't change the lengths. If these were all done with squares, the square would just tip over, right? If I had a square set up with pins at the corners of a square, well, the sides of the square can just both tip over. That can't happen with triangles. So these trusses that we're looking at can be very, very sturdy. Now, what they've done is they've labeled different points, A, B, C, D, E, and we're going to go into each of these and take a look at what forces are acting at those locations. Now, at point, before we get to the individual points, let's do this. Let's take the bridge as a whole. So let's take it as just one object. And if it's just one object, it's being supported from right there, and it's being supported from right here. Now you'll notice in these engineering diagrams, and for those of you who are engineering majors and you're going on and you're taking statics, you'll see this is the way the diagrams get drawn. The intention is that this bridge can stretch out or contract a little bit as needed, and just to emphasize that point, they put it on rollers, right? The idea is we're not going to make this bridge sturdy by putting a bunch of glue here and here. That's not what's making the bridge sturdy. What's making the bridge sturdy is that we've built the structures large enough that they can easily accommodate the forces that they'll run into at these joints. And so we're really, in some sense, looking at the joints themselves and how much force, how durable do the bolts, the giant bolts need to be to hold these structures together. So they kind of go out of their way to show it doesn't come from just making it really, really glued down at this point. Okay, so, and then when we put these pins through at different locations, the pins are not intended to hold the pieces, we're not thinking in terms of holding the pieces together firmly by really tightening down on that bolt. We're really thinking of the geometry and the stress calculations as making this a rigid structure. Now you can still tighten the bolts, right? But we just want to make sure that that pin stays secure in any case. So here is the total bridge, and we've got a force 1 on this side, and we've got a force 2 on this side. And since the bridge is symmetric right now, we're going to say F1 equals F2, and each of those is going to support half of the weight. So half of the gravitational force is supported on the left, half the gravitational support is on the right. Now when you load the bridge, when somebody drives onto the bridge or people start walking across the bridge, that changes things. And so you have to take that into account. But for right now, we're going to say the bridge is symmetric, and we're just dealing with the weight of the bridge itself. And so F1 and F2, they're going to be half of mg. Now when I look at point A, what's going to be happening at point A is the point right there is going to be pushed upwards by the force coming down from the supports underneath. And then it's, our guess is this. Our guess is that it's going to be pulled to the right by this structure right here. And then we're guessing that this structure is going to be pushing down. The stuff that's up on top is probably going to be pushing down onto the lower parts of the structure. So we're assuming that the stuff at the top rests on top of the lower part. Now notice there's different guesses here, and they're actually calling them guesses, but this is just our first guess as to how this might work. So the structure AB is pushing down at that direction, and the force 1 from below, the support, is lifting upwards, and then we're guessing that this is going to have to hold the bridge together this way. It's not going to push the bridge open, but it's going to have to hold the bridge together. This structure is going to have to pull in these side pieces so the bridge stays attached. When we get to point B, at point B, we are, this support structure here is going to be pushing up on B. And so that's listed as force BA. And then here, this is going to be pulling down. So force BC is pulling down on that point. Now if BA is lifting up in this direction and BC is downwards, then BD has to balance those out. And so BD would need to be to the left. And then finally at point C, we have an mg force downwards. Now the mass is distributed throughout the entire bridge, but even in these diagrams we can treat all the mass as if it's concentrated at a center of mass location. The center of mass is up here somewhere. but we're going to take the center of mass force and apply it at point C. These structures are going to have to be lifting up. So these structures can't push down. They're going to have to be supporting the weight of the bridge. And so these to the side are lifting out. Anyway, that's our guesses as to the directions. So let's take a look and see. Ooh, that's what the diagram looks like. Now, once we've solved for the forces at A, B, and C, well, the forces at D are going to match the forces at B. They're just going to be mirror images. And the forces at E are going to match the forces at A. That's just a mirror image also. So we can see which forces are acting. So let's go ahead and start with point A. That's the one that they listed first. And let's go before that. Force 1, at the sides of the bridge are going to have to support 1/2 mg each. And so F1 and F2 are equal to 1/2 mg. Now if I look at pinpoint A, there is a force of F1 upwards, there's a force AC here, and then there's a force of AB in this direction. Now that might not seem like much to go on, right? We don't know a lot about this. We only know what F1 is, but we also know there's only 2 other forces, and we know the angle. We know that the angle right there is 30 degrees. So theta, there it is, theta is going to be 30 degrees throughout. So the only way this could be balanced, given that F1 has to be equal to a known value, well, F1 is going to be equal to FAB cosine theta. So that tells us how much tension or how much compression there is in support structure AB. So AB's force is now known from that force diagram. It's equal to F1 times 1 over the cosine of theta. And then I know, since I knew F1 and I knew the angle, I could determine what FAB was. Once I know FAB, well, I know the horizontal component has to match force AC, so that's what we've written down below. So now we've got all of the forces at point A in terms of force 1. We know force 1 is 1/2 mg, and we know that FAB is force, whatever force 1 is, times 1 over cosine theta. And then with this second formula, the horizontal formula, it shows that FAC is F1 times the tangent of theta. So there was a cosine factor and a sine factor, which leaves us with a tangent. And again, a reminder, the angle is 30 degrees, so tangent of 30 is like 0.577, I think, and cosine of 30 is like 0.866, something like that. So that's just the first pin. Now let's move on to pin B. Now if I look at pin B, this one needs to be, that one needs to be, it is labeled A. This needs to be labeled B. So here, let's see what ones we know. Well, we know what FAB is because we got it from the pin below. So I can use the value from FAB here, and this one can also be divided up into components, and we know all the angles. So we know that because there's only these 3 forces, and these angles match, these 2 forces have to be equal to each other. Okay? So again, it doesn't seem like a lot to go on, but when you realize the constraints that the angles provide for us, and then we can work our way from one pin to the next. And so these 2 forces have to be equal, the vertical components, and that says these 2 forces will have to be equal. We already know what this one is, so now we know what BC is equal to, and the force which is compression. The compression force on BC is F1 1 over cosine theta. So we've got that one. And then finally BD, since we know FAB and FBC now, FB can be solved as 2 times FA cosine theta. and we substituted that in. So we've moved from, first of all, looking at the bridge as one structure to get F1 and F2 determined. And then we moved on to point A, and with just that one force that we knew and the angle, we were able to determine the other two forces. And then we moved on to point B, and by knowing the angles and the orientation of these three forces, we only knew one of the forces, but we knew the other angles. There was only one set of forces that could balance things out given those angles. And so we were able to solve for the other forces. So we're almost there. We're moving around to point C at this point. And so here is the point C at the bottom. Now here, we've got the force of gravity being applied at this point, and we need to be able to support that. So we are going to have, let me go back and look at the original diagram here. So just to get some of these numbers, the bridge is 64 meters long. We haven't used that yet. There is a uniform concrete roadway, and that mass is 1.40, 10 to the 6 kilograms. So that's the mass that we're going to need to be using for this. Okay, and all of the struts are being considered to be massless, and then all the triangles are equilateral triangles. Okay, so yeah, using all that information. So what we've done here is we've got a gravitational force here. We've got these two side forces. Now symmetry says these two have to match, and we've already calculated this one. So FCE matches FAC. Those two are going to cancel. These are going to be symmetric. And so this force is going to match this force. And these are under, I guess they are under tension. And so these are going to be lifting up. I think I said compression before, but these are under tension. These are actually supporting the middle part of the bridge here. And so FCD equals FBC. And then I think that's it. We have solved for all of these is equal to F1. So let's take a look and see what we've got here now. So FBC, that's this one here, its vertical component needs to offset mg along with FCD. So we've got these two, and their vertical components need to match. And remember, this was solved back on pin B and pin A. So pin B is giving us these numbers, and when we add them together, these two forces together equal F1 plus M2, that equals mg, and everything checks out. And so that's how these problems work. You move from one pin to the next. I want to say I don't expect that we're going to be doing any of these problems. This is more, it's an example that the book presents, and the textbook goes through this, but I think for the most part we're going to save this for your statics classes. Primarily we're going to be looking at those, well, all the examples. We had a bunch of examples in that first half of the chapter, and then also looking at the elastic moduluses, the elastic, the shear, and the bulk modulus formulas. Take a look at the homework problems, and I think you'll get a pretty good idea of where our emphasis is going to be. Okay, now here they're also pointing out that here is this bridge that we built, and it, everything checked out on this. And now we got a truck driving over. We're going, oh no, we forgot to allow for trucks to drive across this bridge. We were thinking of just supporting the roadway, but it turns out that you actually have to support the trucks too. And so now what we got to do is we got to go in and look at each one of these struts and add on whatever mass we have placed at different locations. And we have to check it at different locations too, right? As this truck goes from this side to this, what happens with this, the forces acting in each of the struts. So we have to allow. So plan if you're an engineer and you're designing bridges, plan for trucks crossing those bridges. Okay, and so here's some nice pictures. So here's some suspension bridges. I guess this is New York, right? So here are some suspension bridges. I'm guessing, is that the Brooklyn Bridge? Maybe, maybe not. Or maybe I'm flipped around. Maybe that's Battery Park. Anyway, so here is New York City. You've got some suspension bridges in here. And so what's going on with suspension bridges? How are the stresses set up for those? And so for a suspension bridge, remember we've got structural pieces that could be under tension or they could be under compression. If I've got a suspension bridge, let's take a look right here. So this suspension bridge right there, is that where is the compression and where is the tension taking place? So if I were building that bridge, I would start with the towers, right? We build the towers, anchor the towers firmly because kind of the whole bridge is being supported by those towers, all right? So the towers go in first, and then what we start doing is hanging some of the cabling between the towers. So if you go back and you search construction on some of these bridges, and a few years ago there was like some anniversary of the Bay Bridge and then an anniversary of the Golden Gate Bridge, and they great videos and photos of the construction process, seeing the steps that they went through. So you start hanging all these cables. Now the cables are designed not to be under compression, right? I can't have a cable that's under a compression. So the towers get built, cables get hung, and then the roadway is being supported by these individual cables, which are also under tension. So the roadway is being supported by tension in all these cables. The tension of all of those is transferred to these arching cables, and then the force is downwards on the towers. So the tops of those towers are supporting all of the weight of the roadway that's been transferred through the cabling up to this point right here. Okay. Now, so that's a really pretty bridge. A few years ago, I was walking by the Trader Joe's in El Cerrito, at El Cerrito Plaza, and at that time, I don't know if they still have the drawing up there, but on one side of their building, they had somebody come in and draw the Golden Gate Bridge. I'm sure that's what it was. I'm pretty sure that's what was intended. Was the Golden Gate Bridge, and then it was sunset underneath the Golden Gate Bridge. So they had the Golden Gate Bridge. They had the structure set up, and they had this nice sunset underneath it, glowing. But the artist, whoever drew this, decided that these towers were kind of blocking the nice view of his artistic piece or her artistic piece that had been set up. So they decided to leave the towers out. So if you ever happen by El Cerrito, Trader Joe's, walk around to the north side, see if that, it's been a few years since I've seen it. I haven't been over there recently. But see if they've changed this, but these towers were not there. So they had the roadway going all the way across, and then they had all this nice cabling going across, so the bridge was beautiful, and they had this nice sunset picture with sunlight glowing outwards, but they left out the towers, and the towers are what's holding up the entire bridge. So I had to cringe a little bit when I couldn't quite look right at it when I walked by, because it looked pretty terrifying. What would happen if we took out the towers on a suspension bridge? So anyway, you have to check for those when you're in engineering. Here's an example. The book kind of wraps up the chapter with just some interesting photos. These structures have survived thousands of years, and look what they did. They took the stones and they built an archway. And when you build an archway, what happens is all of the stones compress against each other, right? All these stones have gravitational forces acting on them, lifting, tending to make them fall. All these stones are going, oh, but I want to fall. There's a gravitational force, but they can't because the neighbor stones are in the way. And this stone can't fall because there's a stone here, and this one can't fall. So there's no way they can all fall together, and so they're stuck right in that archway. And there are just so many structures, you see these, that have survived thousands and thousands of years very successfully by using a simple idea of compression. And here's the diagram that goes along with it. So with those stones, you build a wood support, and you lift up all these stones and you put them in place, and then you remove the wooden structure underneath, and they stay there because they're stuck. The stone at the top can't fall because it doesn't fit through this opening. And these are not going to move out of the way for it because they've got forces acting, pushing them down also. So you build the scaffolding, you put in that arch, you build a bunch of stuff up on top, you take out, that must be exciting when you're taking out the support structures from below, but the stones all stay in place. So, using compression to an advantage. Now what you might worry about, not with this building so much, but I'm trying to find a better, here we go. We need just an arch by itself. I thought we had one here. What will happen, let's go back to this one. This is probably as good as we're going to do. So if we didn't have all this stuff surrounding it, if this was just an archway itself, what would happen is you made it larger and larger. The sideways forces would begin to push things to the side, and you could still end up with a collapse. So the solution to that, one of the solutions that architects came up with, was to use a flying buttress. So look at this. Here is this building. So they build it up, and then they build it together. Now, the forces up here are going to tend to push the walls outward. And so what they've done is they've built extended flying buttresses to hold those walls so they don't collapse outward away from that building. So if you get a lot of stress on these things, eventually those horizontal forces can overwhelm your structure. So you can put in a few flying buttresses to take care of that. Also, they're showing here that if you look at some of the forces, this is, again, just kind of informational. If we have a lot of force acting here, we're going to need some horizontal forces to hold these structures into place. What we can do is we can do better if we change the shape. A rounded arch works better. Here we are. Here's an enormous dome. And you can imagine that once you get an enormous dome built like this, then there's going to be large horizontal forces from all of these blocks pushing against each other. So everything here is under compression. And that's it. So that wraps up chapter 12. So I guess we will stop right there. That's a nice last picture. So if you guys have questions on anything, stop by. There's a nice picture of the sky up there, but when it rains, the water comes through. If you guys have questions on anything, stop by. So lots of office hours. Stop by with whatever questions come up.